Hello friends, Namaste, all of you, Namaste everyone, and myself, Xiisci Takalkar, of course, was Trinity sir. Dear friends, your congratulations and I wish you have a conductivity day today. I means we have to conduct well, we have to conduct properly. Okay. Dear friends, specific conductivity and molar conductivity. Before going to study these two very important points, let us discuss about some basic laws. Okay. As you know, the metallic conductors, that means the metals. Why the metals? Because there are free electrons, that is valence electrons or mobile electrons. And according to the band theory, the conduction band and valence band, there is no gap. The forbidden gap is said to be zero, or it is always less than 3 electron volts. So here in the metals, the conductivity can be explained on the basis of band theory, but in fact there are 3 mobile electrons are responsible for the conductor. Now consider Ohm's law. This law gives the resistance of that particular conductor and the current or electricity flow through the conductor and voltage applied across the conductor. So this is in ohm, also denoted by symbolically like this, and this is in ampere and volt, and this is in ohm, or symbolically can be written. Okay. Or one can also the resistance of that material is equal to V upon R. So here the units are important. They are always in amperes. So here the voltage applied across the conductor, current flow through the conductor, and the resistance of that material. Now, why the R, that is the resistance of the material, differ from material to material? Because you know there are kernels and electrons. Okay. According to the C model, the kernels are the atom nucleus, stable one, and the electrons they move from one to another atom. So here, during the temperature increases, the electrons collides with the kernels and the resistance also increases. So in this case, the resistance increases with the temperature in the metallic conductor. Okay. Now let us consider the next point about the conductivity or conductance. As you know, different materials, for example, metals are good conductors, where non-metals are bad conductors or no conductors, and it depends upon the free electrons. Okay. Now the resistance denoted by R, as you know, it is actually the directly proportional to the length of that conductor and inversely proportional to the cross sectional area of conductor, and this is the length of conductor. Generally, common, not SI, commonly is in centimeter and area, that is the centimeter square. So further, this R is some proportionality constant rho. This is called as and this rho is the specific resistivity of specific resistivity. If L is equal to 1, A is equal to 1 centimeter square or whatever, 1 centimeter. Therefore, this rho are A upon L, and for this R is equal to 2. So that means one can define this specific resistivity. It is the resistance of unit Q material. What is unit Q? That means if you consider your conductivity cell, there are two cells. Whatever material is inside of these two electrodes, suppose this is the one electrode, right, and this is the another, okay, attached like this. Then the length between these is 1, and the area of is also 1 by 1 by 1. So this is nothing but 1 centimeter cube, and this is also called as a 1 mm value. This is the unit of value. So here, whatever material is inside of these two plates, two electrodes, and having a total value that is 1 ml, that is 1 cc, cubic centimeter, that is called as the resisting. Specific resistivity can be defined as the resistance of unit cube material. That is 1 centimeter or 1 ml. Okay, like this, or similarly, one can also consider the conductance. It can be denoted by G or also denoted by capitals. So now the conductance of the conductor is directly proportional to the cross-sectional area and inversely proportional to the length of the conductor. So here, if there is a copper wire, more is the length, this conductance decreases, or the smaller the cross-sectional area, smaller is the conductance, or if the wire is thick, that is cross-sectional area is high, then the conductivity is shown to be a high. Okay. Now this can be further equalized, taking a proportionality constant, what is called as a kappa, A upon S. Here, A is equal to 1 centimeter square and L is equal to 1 centimeter. That is the value is equal to 1 by 1 by 1 centimeters cube. That is 1 ml. So whatever material is in 1 ml or 1 centimeter cube, right? So here therefore this can be equal to K. So this K that means what is K? Where K is specific conductivity. Oh, very good. Specific conductivity can be defined as definition. Of K. It is the conductance conductance of unique cube material. That is, of course, 1 centimeter cube. That is 1 mm. So whatever material is in 1 ml, the conductivity is said to be its specific conductance. Okay. Now, secondly, in general, if you consider conductivity set, okay. So what is it? In practice, there are two such electrodes like this, and this is 1 by 1 centimeter, and distance of their separation like this is also 1 centimeter. So this is nothing but the 1 ml value like this. Okay. So this is the one electrode, and this is the another electrode, and it is dipped in a solution. So whatever ions are in between this or in this 1 ml of the material, right, that conductance is its specific conductivity, right? The ions in between this one, right? This is the one. Okay. So here, but right, this is the 1 by 1 centimeter square, that is 1 unit. Okay. So whatever is the conductance of that material in 1 ml of the substance, that is the specific conductivity K. Okay. Now, in practice, in the construction, preparation of the conductivity cell, this distance sometimes may be changed, maybe more or maybe less than 1 centimeter. That is a manufacturing error may be there, and therefore a conductivity cell that you are going to consider, because of this error, to avoid the next values, we have to consider a cell constant, and it can be defined as the ratio of the length of separation of these two electrodes having a cross-sectional area or length into length. Okay. So L upon L, that is the cell constant. It is denoted by B. So B is equal to L upon A. Okay. Okay. Now consider this thing here. How it relates. So here, if you substitute the values R is equal to the specific resistivity L upon A, or this can be equal to B R. Okay. Or in this case, one can also write here G is equal to the specific conductivity A upon L. This is nothing but the A upon L, that is 1 upon B, or the G into B is equal to. So here the specific conductivity can be given by this way. Okay, this is the conductance of the conductor. This is the cell constant, that is the L upon A. That is the separation distance between the two electrodes having a cross-sectional area A here. Yes. And K is the specific conductivity. Now what is the units? Consider units. Now you know R is equal to rho, or this specific resistivity. So here rho is equal to, one can put here R. Okay. Now here A upon L. Or here this has a unit of over. This is the input. This is the centimeter square upon centimeter. This is the ohm, or symbolically can be write as ohm. Okay, ohm, and this is the centimeter. Okay, so here ohm centimeter is the unit. That means the specific resistivity can be defined as here. That is the resistance of the material unit 1 ml material. Resistance of the 1 ml material. That means L is equal to 1, A is equal to 1, or that is the total value becomes 1, and that material has some resistance, that is the specific resistivity. Okay. Similarly, in this case, one can write here, therefore, K is equal to G L upon A. Or what is this? This is the conductivity, that is the opposite of the resistance, and having the moles. Right? Length 1 centimeter and 8 centimeters. Okay. So here this can be denoted like this centimeter, and this getting cancelled into the centimeter inverse. Okay. So here kappa, the specific conductivity kappa has the unit moles. Okay, centimeter. And here the ohm centimeter. Okay. This is the specific resistivity, and this is the specific conductivity. Okay. Now, what it means? What it means? Specific, the word specific resistivity or specific conductivity. It is nothing but the conductance, but only unit value, material in a unit value, and common are generally considered, not a meter. SI unit is not considered here, in a centimeter cube, that is 1 ml. So whatever is the material in 1 ml, and its conductance is nothing but the specific this conductivity. It is the nothing but the conductance of unit cube material, that is 1 cc material, cubic centimeter, or 1 material. Okay. Now, what do you know about the K? As you know, the unit is mole centimeter inverse. This is also denoted as centimeter inverse. Very important. Or capital S centimeter inverse. Okay. Now the S centimeter inverse is the unit. Secondly, the specific conductance, specific conductivity means the conductance of unit cube material, that means this is the 1 centimeter by 1 centimeter by 1 centimeter. So whatever is the material inside, it may be a ionic conductor or it may be a metallic conductor. Whatever is the material inside of 1 ml value, right? Gas conductance is the specific conductivity kappa. Read as kappa. Okay. Now, as the temperature increases or concentration varies, of course, the number of ions, if you consider the solution, right? If you consider the solution, then if the more is the concentrated solution, there will be more ions, right? So this is suppose the conductivity cell, one plate, and this is another plate or electrode, and here it is further one can measure. So in between this 1 ml value, there are the number of ions, and if more is the concentrated solution, what it indicates, more ions will be there. If it is a dilute solution indicating less number of ions, and it means more conductance. That is more will be the specific conductivity. Okay. So here K, specific conductivity, depends upon the concentration. Depends. Okay. Kappa depends upon concentration of the solution. Okay. Secondly, it also depends upon the temperature. How? Because same concentration is taken, and if there are variation in the temperature, the with temperature value increases and number of ions at higher temperature decreases, and therefore there is a variation in the conductance or specific conductivity. But at the same time, as the temperature increases, the dissociation of the electrolyte also taking place. Dissociation, right? As the temperature increases, the interactions between the solute and solvent molecules in a solution going to change, and dissociation taking place, ion becomes free. So the taking consideration these two criteria. Okay. Now how it relate, how the relation between the different conductors with the help of molar conductors. Okay. Now consider the very important point, that is the molar conductivity, and it is denoted by here, cap. Okay, region cap. Now, as you know, this is depends upon concentration. Okay. Now, the molar conductivity, let us consider from the definition. That is the conductance of 1 mole of substance. 1 mole of substance. That means the substance is fixed. If you consider one of the example, sodium hydroxide is a electrolyte. What is electrolyte? When dissolved in water, it ionizes and giving ions. Okay. So here NaOH, what is the molar mass? That is a 40 gram molecular mass of NaOH is 40. Now this 40 gram can be dissolved in 1000 ml, can be dissolved in 500 ml, can be dissolved in any value 2000 ml. Okay. So here the total is 40 grams. So here if the solution becomes more concentrated than the solutions, so here if you consider the solution, the K is high. But value is low. If you consider the extreme case, and if you consider this case, what is about kappa, that is the specific conductivity, is low, but value is. What happens with increase in the concentration or decrease in the concentration? The concentration is lower here because volume is high. Same amount is dissolved in 1000 ml, same amount dissolved in 500 ml. So twice the difference in volume. Therefore, in this case, the concentration is high. That means number of the ions in this unit tube is high. Right? There are more and more number of the ions here. Okay, more and more number of the ions here. And if you consider that same conductivity cell, here is only less number of ions. So specific conductivity is low. But what is about the product? K into V. K into V, it is expected to be same for this case or this case. That means if you consider the molar conductivity, it is the conductance of 1 mole of substance, right? 1 mole of substance. Whatever is the, and that substance, okay, 1 mole of the substance, and it is placed in between two electrodes large enough to contain all the solution for the measurement. Okay. Now, in practice, it is not possible to make the electrode so big in size, so large in size. The conductivity cell is small. So, we are going to measure the conductance of only 1 ml of the material, and we are going to determine, we are going to calculate how. So on the basis of this, it is clear that the molar conductivity gap is given as the specific conductivity into V. What is this? This is the specific conductivity, and it is in 1 ml. Whatever ions, all the ions, they are in 1 ml solution, in 1 ml solution. Okay, that is the conductance of 1 ml. Conductance of 1 ml of the substance, of the material. And what is this? Value. Of course, the volume containing 1 mole of substance. But this value is in ml. Okay, value in ml. Of course, in ml. Okay, and therefore we get the total conductance of the 1 mole of the substance, whatever is the solution. Now if the value is high, the K is small for the 1 mole, and if the K is high or the concentration is high, K will be high, value becomes less. The product is expected to be a very constant. Okay. So molar conductivity is nothing but the conductance of 1 mole of the substance. Okay. Now further consider what is molarity. As you know, the concentration of the electrolyte is measured in a. This is one of the very important unit of the concentration, molarity. M. What is the definition? That is the number of moles. Number of moles of the electrolytes divided by the volume of solution. That is N upon P in liter. Volume of solution in liter. Number of moles per liter of the solution. Per liter of the solution. Now, for the molar conductivity, N is equal to 1 mole. Okay. Or this can be, therefore, N is equal to N upon P liter, or P in liter is equal to real N upon M. What is M? That is the molarity. That is the method to express the concentration of the solution. Okay. So here P liter. How you convert into the ml? Therefore, multiplied by as you know as 1000 ml is equal to 1. Therefore, this can be converted into the ml. Here 1000 into P liter, or in this case it becomes the in ml. This becomes ml. That means N upon M into 1000. Okay. That is P in ml is equal to 1000 into N upon molar concentration, or N is equal to 1, that is 1 mole, therefore 1 mole. And this is what is the molarity, or this is nothing but 1000. And now, okay, right? 1000 M. Where M is the molarity. N is the number of moles, and for the specific or molar conductivity, only 1 mole is considered. N is equal to 1 mole. So here one can substitute the same values in this formula. Okay. Therefore, what is we get? What we get? Oh. Therefore, consider the molar conductivity. Therefore, is equal to, as you know, kappa into the, this is the conductivity for 1 ml, conductance of 1 ml, and this is the conductance. This should be in ml, or this can be therefore the into the P is equal to, now here in ml 1000 upon m, and this is the molar conductivity. This is the molarity of solution of electrolyte. Okay. Right? Now, further, this is very important in mind. Sometimes this symbol of cap is denoted as capital M. Why capital M? That is molar conductivity. Okay. So here may write here capital M, cap M, capital M, molar conductivity. Okay. So here Pn, that is the molar conductivity. Okay. Now consider. One can write here the molar conductivity, or this can be further as discussed here 1000 into K upon molar. Okay, molar. Now, equivalent conductivity. Equivalent conductivity. One more. Here the E. Instead of molarity, the normality is considered. Instead of molarity, the normality is considered. That means this can be therefore 1000 into kappa. Molarity consider the normality. Normality means the number of gram equivalents per liter. This can be other. Molarity. What is molarity? Number of moles per liter of solution. And what is normality? This can be other. Number of gram equivalents per liter of solution. Right? Okay. Or further consider this equation 1 and how they relate. Here we can upon and into this P. This is 1000 K into P into the pound. This the gram equivalent weight. So gram equivalents are your values. Now one can relate the molar conductivity and the ratio. So we can consider this the 1000 into K into P of liter upon 1000 K, right? And here upon N K, right? And this P liter upon P. So this getting cancelled. Only one can get P upon N. Okay. So this is the equivalent weight. Upon number of moles. These are the moles. Equivalent weight means one can number of moles, that is the W upon N. And here the equivalent weight, that is the W upon K mass. Okay. Or W getting cancelled. This can again M upon P. Okay, so here the molar mass and equivalent mass, the ratio, and as you know, this factor is said to be the molar and equivalent mass. One can get molar mass upon equivalent mass. This is the molar mass upon equivalent mass, and their ratio is found to be some factor F. For example, consider for acid or base or salts. So here, if you consider HCl, the N is equal to E is equal to 36.5. So here N upon E is equal to N. If you consider H2S support diacetic acid, molar mass is 98, equivalent mass is 49 because there is diacetic acid, so 98. They want to return to 49. Therefore, N upon E is equal to. Or similarly, for sodium hydroxide, M and E are same. Therefore, F is equal to 1. Or if you consider magnesium hydroxide, it is a diacetic base. So here the F is equal to 2. If you consider aluminum hydroxide, F is equal to 3 because molar mass and equivalent masses are different. Or if you consider the salts like copper, then F is equal to 2, or silver F is equal to 1, sodium F is equal to 1, or if you consider aluminium, then F is equal to 3, etc. Or chloride F is equal to 1. So here one can establish the relation between the equivalent conductivity and molar conductivity in this way. Okay, dear friends, we are going to stop here. Thank you very much.